Hello, and welcome to the third video of Worksheet 6. As you can probably tell, I'm recording this one on a different day as I did the previous two because the last two took a long time and I didn't want to do this one. Anyway, so we're doing the final part of this worksheet. We're doing this runtime problem. We're just looking at best case and worst case. So let's try to keep everything in mind that we did in problem 2 about how best case and worst case actually works, and then take a look at solving this problem. There's a decent amount of code here. Most of the types of these problems you see will not have this much code, but it's good to kind of manage the complexity and do a bigger problem. So first of all, this method, it tells us right out what we do with this method. It basically says it returns true if every int has a duplicate value in the respective array and false otherwise. So if you have an array and it looks like, this, you would return true because each element has a duplicate. And if it looks like this, you would return false because each element does not have a duplicate. I think, by the way, something like this, I believe would also return true, but don't worry about it that much. Okay, so we want to figure out what the best case is and what the worst case is. So keeping in mind what we talked about in terms of best case and worst case in the last video, we know right off the bat that best case and worst case are both going to be in terms of theta. So I'm just going to go ahead and write them there. They're always going to be in terms of theta. Even if you don't exactly understand why, you can just remember best case, worst case, always theta. Okay, so let's start looking at this function. So we have a sort subroutine right here, and we know that it runs theta of n log n time. In general, sorts run in n log n time, which we will learn towards the end of this class. But for now, you can just assume that. Okay, so let's go through and let's first look at kind of the best case here. One thing to note is we are inputting an array, and usually when we input an array, the n that we're talking about in terms of runtime is the length of the array, which is the case here, right? We see int n equals array.length. Anyways, so first things first, I see we sort the array. This takes n log n time, right? And we have to do this every single time we run this function. So right there, from the very first line of this actual function, we've already made our best case at least n log n. It can run no better than that because we have this kind of dominating operation that happens. So now basically what we're looking for in the rest of the function is, do we have anything that's going to take longer than that? Because remember, we only include the biggest single standalone term when we're talking about runtime. So if it turns out that the rest of this all runs in, say, constant time, I'm not looking at it yet, but let's say it does, well, then the runtime is still n log n because we're dominated by this first operation. However, if this over here runs in, exponential time or something, then we're dominated by exponential time, and this doesn't matter. If it runs in n log n, it's still n log n, right? So we know best case has to be at least n log n right off the bat, and obviously worst case has to be at least n log n too. Okay, so now let's look at these interior loops. So I see we have the classic, a double for loop, which is something you see a lot in these kinds of functions. So I'm going to take a look at the broad pictures of these for loops. First of all, I see this first for loop is your classic, just I equals 0, I up to n, iterate. So this is designed to run in n, but we don't know that it runs in n for sure. And in particular, I'm going to look at the other parts inside this for loop to determine if this is really an n for loop. So one thing I see is this is just a quick operation. This is a second interior for loop, so I'm not going to worry about it yet. But I see here we have this if does not have duplicate, return false. This is a very important line because what it means is that even though this for loop can run in up to n time, if, for example, we hit this if condition and immediately break, then it doesn't run in n time, right? If the loop only runs once, it's constant time. So I'm going to put a question mark here. Like this can run up to n, but not necessarily n, right? Another way, if you want to get really technical, is you could think of it that this runs, this particular loop runs in this runtime where it is lower bounded by constant time. That's the case we just break immediately, and it's upper bounded by O. That's the case that we go all the way through. That's a more technical way to look at it. But anyway, so I know that this runs maybe in n, but we don't know for sure. And then I look at this interior for loop. So this interior for loop is also an n for loop. We just start j at 0, 0 goes up to n, j increments by 1 every time. That's your classic linear search. And then what I see is basically we have an if condition. I don't really even care what the if condition is. All I know it's an if condition that takes constant time to evaluate. And then I see it sets a variable to true. So keep in mind, this interior for loop has no way to break early, right? No matter what the values are inside of the array, there is no way that we run this interior loop less than n times, right? So I know that this for loop in every iteration, best case, worst case, whatever, of this function is going to run an n time. So I hope, I'm going to take a second right here to step back, and I hope you see what we've done. We said, okay, we know that we're always going to have an n log n here. We know this loop is always going to run an n, and we know that this loop can run an n, but because we see there's this weird if condition here, it might not necessarily. And in general, when you're looking at best case, worst case analysis, if conditions which lead to breaks or returns are usually where like the kind of logic of best or worst comes in. Okay, so now let's think best case. So in best case, we're minimizing the number of operations we do. Again, we have this n log n here. We have this n, which always runs an n time, and then the total runtime of this 2D for loop is going to be determined by how many runs this outer for loop does. Again, we see here that we start has duplicate at false. We might set has duplicate to true in the interior for loop. And then if it does not have a duplicate, we return false. In other words, in the best case, this exterior for loop is only going to run once, not n. So it's just going to be constant, right? So this is also, if you want to think of it kind of in terms of the actual array we're putting in, if you look at the operations, this is the case where the first element doesn't have a duplicate, right? If you have something like this in the array, first things first, we're going to sort it. We're going to sort it. That takes n log n time right off the bat. Then we are going to basically look at the first element, look at every other element, which takes n time, say, oh, there's no more ones, return false immediately, right? So that takes n log n time. And we can also see it here. We have a runtime of n log n to sort plus n to do that first scan. We only keep the highest term, so we end up with the best case of theta n log n. Okay, that's the first part. Another thing to keep in mind is notice how I didn't actually even draw this array until after I figured the runtime out, because you don't need to, right? You don't really need to understand what this if condition is doing. All you need to do is look at it and say, yes, this is an if condition. It takes constant time to evaluate, and that's pretty much it. That's a tip I would give you in general when it comes to analyzing these types of functions, is sometimes you don't really even have to know what the function's doing in order to actually analyze the runtime. Okay, so we know that the best case is n log n, so the worst case has to be at least n log n. So let's go through again and see where things are going to be different. So again, this n log n and this n happens regardless of what the input array is, so it's going to take at least n log n. The only thing that could differ between best and worst case is this right here, this n. We said in the best case it runs in constant time, and I think it should be fairly clear that in the worst case it runs in just n time. Why is that? Because in the worst case, basically what we do is we go into this loop, then we go into this interior for loop. It never sets, or it does set has duplicate to true, and if has duplicate is set to true, we don't hit this if condition, and then we just go up and we iterate again, again, again. We do it n times, right? If you wanted to look at this in terms of an array, let's make this a length 6 array. This would be the case where you end up with duplicates of everything, because basically what's going to happen is it's going to start at 1. It's going to look at every other index for another duplicate, and it's going to find one. Then it's going to go to this one. It's going to look at every index for another duplicate. It's going to find one. It's going to go to this one, look at every index for another duplicate, et cetera, right? That means that we are looking through every element, which takes n time, and we're doing it n times because we're doing a 1 for each element. Notice this is not the most efficient way to do this, right? Because the second that you find there is a duplicate of 1, you don't have to check if that duplicate also has a 1. So there's some optimizations we might have here, but explicitly the way the function is written, that is going to give us an n time. So now we have a for loop that runs an n, and we have an interior for loop to that for loop which runs an n. So these are basically going to combine to give us an n squared. So the worst case overall is going to be an n log n plus n squared. That n log n goes away because it's dominated by the n squared. So our worst case ends up being just theta n squared. That's basically how we do that. So then the next part of this question is basically, okay, we want to find a way to run no uniques that runs in n log n time. Okay, so now let's look a little bit at no uniques as a whole. So no uniques has a best case of n log n. It has a worst case of n squared. That means if you just wanted to describe the no uniques in terms of data notation, or you could basically say that it is lower bounded by n log n, and it is upper bounded by n squared. This particular function is. Again, this Although the omega, the lower bound, is related to the best case, it itself is not the best case. Remember, the omega bound is saying it runs in at least this time, whereas the best case is saying in the best case it runs exactly this time. So these two things are related, but not exactly the same thing. Same goes for O in worst case. But in this case, I think it's pretty clear that we want to make this function run in theta n log n, right? When does something run in n log n? It runs in n log n when both its omega and its O are n log n. And right now we see its O is bigger. Whoops. Right now we see that its O is bigger than n log n. In other words, the goal of this problem is going to be to reduce the worst case runtime of this function to n log n, which will therefore reduce the upper bound that this function could take to n log n. And then if this and this are both n log n, then it runs in theta n log n. Okay, so now let's target, where does that happen? Well, we see right here, these two for loops are what gives us the n squared runtime, right, unavoidably. So what we need to do is figure out a way to turn these two for loops into an operation that takes n log n or less time, right? Why or less time? Because we're already hard bounded by n log n up here. So if this turns into constant time, the runtime is still n log n. But let's set our goals a little more modestly and just go for n log n. Okay. And so then this is where you actually need to understand the function a little bit and ask yourself what's going on. So remember, we have an array. It has a bunch of elements in it. It might have some duplicates, and we want to see if it has all duplicates. Okay, but there's a very important property about this array, and that's that it is sorted, right? We sort it right at the beginning. The array is always going to look like this. And keep in mind what we're doing is every time we are looking at an element, we are searching the array for a corresponding element, right? Okay, so we could just linearly scan through and look at every element, but because it's sorted, we can take advantage of that and do something else. We can run a binary search. You should be familiar with binary search, so I'm not going to go over it. If you're not, I believe the BST lab has a big explanation of binary search. But basically what it is we can take advantage of the properties of the array to use a fast runtime. So binary search does not take n time, it takes log n time to run. So when would we do the binary search? We would do it here, right? Because this is the for loop that is actually running through the array and checking for duplicate elements. So instead of checking naively just all the way down, we can do it with binary search. So just, pretend that this was binary search. That would take log n time. And now in our worst case, this is still going to run n times, but this is going to run log n times. So now basically our worst case is, instead of what we had up here where it was n log n plus n squared, it's now n log n plus n log n. N log n plus n log n is just n log n. That means that our upper bound on the function is now going to be n log n. And if the upper bound and the lower bound are the same thing, that means you can establish a theta bound, a type bound of n log n. And that's basically an optimization you could do. So basically the way to make it faster is you change this naive linear search into a binary search, taking advantage of the sorted properties of the array, and that'll give you a faster runtime. There are faster ways to do this. When we learn about sets and maps, we will learn about a way you can do this in linear time even. But for now, that's all we need to do. So I hope this makes sense, and goodbye.